computational methods. But the idea is this. I have a bunch of data. And I don't necessarily know what the equations of motion are. Maybe the system's too complicated. Maybe I just don't understand it. So for instance, in biology, you don't have an F equals ma to work with, right? You don't have something like that to hang your hat on. And so on the other hand, there's some prescribed behavior that is always observed. And so the idea is, can I empirically construct some kind of equations out of that? Okay? So the idea of the course is to do just that. Take data, analyze it, come up with some constructive rules of how to do that in a meaningful way, in a statistically relevant way. There's three main things that are going to be combined together here. First is statistics. Okay? Fair enough. So we're not going to go, you know, I mean, look, there's a whole statistics department here, and they get very serious about this stuff. Okay? What we're going to do is sort of be casual statisticians, but we'll know enough to understand how you use some of these principles and apply it to the data analysis that we're going to do. Two, let's call it Fourier methods or spectral methods. We're going to learn a lot about time frequency domains, taking your data, Fourier transforming it, looking at the spectral content, analyzing that spectral content, using statistics to tell us something about that as well. And finally, the one that you actually probably feel fairly comfortable with, which is linear algebra. So the idea is if you combine these three little things together in sort of clever ways, turns out you can extract quite a bit of information from given systems. In many ways, people work a lot on this in different areas. So atmospheric sciences does a lot of this, oceanography, biology. A lot of people are starting to use a lot of these techniques nowadays towards analyzing their data. Okay, so one of the problems with that is that right now there's not a, if you notice on the web page, I should probably give you the web page, right? Is that a good idea? I'll email it out later. How's that? But one of the things that is a problem with this is that there's no textbooks for this course, really. So there's no standard text on using these methods together. Some of the things we're going to be doing here is principal component analysis, proper orthogonal decomposition. We're going to do time frequency analysis, image processing, all kinds of applications of data using these basic techniques underlying it all. Okay? So that's the thrust of the course. MATLAB is going to be our primary tool to do. And I think we actually have some really cool homework lined up. Okay? So I think I say that I think that because you know, nobody's done it yet. So, and this is the first time the class has actually been taught. It's a new course. So the hope is that it's super awesome homework and you learn a ton out of it. But of course, we could crash and burn. I don't know who we'll blame in that case, but we'll find somebody by then to blame for that. Okay. Questions at this point? Okay, let me say a couple comments first about grading. I haven't quite figured out exactly what I'm going to do for grading yet. There won't be any exams. Mostly it's going to be those homeworks. And then at the end, I think I've decided in the last 3 or 4 weeks, you'll do a project. So you'll pick something in teams of 2, 3, 4 people. And what you'll do is you will basically pick out either a couple papers and take the ideas in those papers that's perhaps related to your area of interest, whatever that happens to be. And then you'll take that stuff, take the data, apply some of these principles and ideas that we've been using over the quarter, and write up a report with 2 or 3 of people. Okay? That's what we'll do. That will be one piece of it. And in addition, there's super cool homeworks along the way. Some of them will involve iPhones. It's going to be awesome. Who has iPhones? We need at least 3 of them. I've got one. 2, 3, 4. No, you have to, you know, the reason you have to have an iPhone, besides it's super awesome. I like my iPhone. Anyway, it's got a video camera, and we're going to take data with our video camera directly. It's going to be an awesome experiment. We're going to do it hopefully right here in class later on. I bet you can't wait. See, now you're all I'm excited about it. See, this is just like the previews of the movies, you know? I just gave you the good previews. Now we have to watch the boring movie. But the previews make you think maybe there's a good movie coming. But I gave you the best scenes right there. All right, any questions at this point? Okay, so we're going to start here for the first week. And in particular, what I want to do today is do a little review of, so actually this first week, what we're going to do is today I'm going to talk a little bit about basic probability concepts, with the idea that tomorrow, on Wednesday, we move into some of the statistics ideas, and Friday we end up with the idea of hypothesis testing and the ideas of what makes things statistically significant. Okay, so but it's important to put the mathematical framework down. Some of it will hopefully all be review. But when was the last time you took a statistics or probability course? Probably, maybe it's been a while. Now, if you're a statistician, you know, you can take a nap. Back row. For everybody else, you know, it's always good to review. Have these in your mind. And of course, we're going to flip lots of imaginary coins, right? That's what you do when you talk about statistics. Okay, so let's start off with simple ideas from statistics. And then what we'll do, especially on the next couple lectures, is talk about some of the built-in MATLAB functions that are there that are accessible for you to just do with your data. Okay? So we start off with basic probability. Okay, some things are not quantifiable, like the probability that you might get something out of today's lecture. Right? The hope is that it's high, but it could be low. Who's expecting to get a lot out of this today? Nobody. Awesome. So I'm starting off on a perfect place, so I cannot go lower. See, I was hoping nobody would raise their hand, because then all of a sudden they'd have all these expectations. Okay, so we start off with no expectations, and we can only go up. So let's start off with the idea of sample spaces. And we'll denote this by S. So typically, the sample space is going to be the space of all possible events that can occur on a given experiment. Okay? By the way, oftentimes you don't know this. All right? In realistic experiments, you don't know what the sample space is. However, by clever framing of the problem, you can come up with sample spaces that will fit your way of thinking about the problem. Okay? Now, let's just come up with some examples just to put this in perspective. So here's one example. If it involves flipping a coin. Okay, so if you're flipping a coin, then the sample space, you can either get a heads or a tails. Now, I don't know if anybody of you have ever flipped a coin, landed it on its edge. If not, we're going to stay with this. And you have to show me you can do that before I put it on there as a sample event. Okay? All right. Heads or tails? That's your sample space. Those are the possible outcomes of a flipped coin. Okay? All right. What about two coins? Right? So these are obviously very simple examples, but hopefully you'll bear with me through this because I think this is all important to put out there. And there are your possibilities. If you flip two coins, you could get two heads, two tails, a head in the first coin, tail in the second, or a tail in the first, head on the second. So there are four possibilities, four outcomes for this event. Okay? If you don't distinguish between the coins, which is coin 1 or 2, it looks like these two are the same. But in the experiment, it's important to know that there are two distinct coins. Okay? Same thing, roll of a die. The sample space includes, you could get a 1 or a 2, 3, 4, 5, 6. Okay? Over Christmas, I have a different kind of die. It has SpongeBob SquarePants on it. So that would be a different sample space. There's Krusty Krab, SpongeBob SquarePants. I have kids. They're 7 and 4, and they love that stuff. So there we go. But we'll just stick with the regular ones. There we go, 3 1 through 6. Okay, so those are the possible outcomes, right? So very simple idea. Sample spaces. You always have some space on which events occur. And the idea is that what we want to talk about is events occurring on some sample space. Okay? And then we're going to talk about the probability of those events occurring on those sample spaces. Okay. So any subset of the sample space, I don't want to spell out that much, is an event. We'll denote it by E. Okay? Now, so for instance, I could define an event as the following. In a coin flip, so this is going to relate to my previous example that I just gave for sample spaces. I could say, I want an event to be that I get a head on a coin flip. So in that case, that's how I would denote that. Okay? If I flip 2 coins, then I can, for instance, define an event where what I want is heads on the first coin. Okay, and that's how that event would be defined right there. 2 coins, I flip them. All I'm looking for is the first coin to produce a heads. Okay? Or I can define an event. If I toss the dice, I can define an event as getting a 2, 4, or a 6. So in other words, I toss the dice, I get an even number. Okay? So these are just all possible events that may or may not be of interest to you. Okay? Obviously, if you're gambling, you care a lot about dice tossing, let's say. If you're playing some games, is it craps you play dice, right? Lucky sevens, right? What else do you get? Is it that just lucky sevens? What else do you want on? Come on, help me out, Chris. What else do you want to throw?
Play dice.
You want to play dice? You don't want snake eyes, right? Double ones, that's bad. Is that bad?
7's actually bad.
7's bad? What's good?
Well, it depends what you bet on.
I suppose I bet a lot of money on something.
If you bet on 11, then you won 11.
I want 11 if I bet on 11. So yeah, why do they always say lucky sevens?
It's not craps, because that's when you lose your money.
Okay, that's when you lose your money. You gotta write that down. Lose your money on craps. That's not in the notes, but that's good advice. Okay, so these are all events that you define, and eventually we want to find probabilities of these events happening, right? Ultimately, you know, these are very toy problems, but part of what we're trying to do is set up the mathematical framework. Remember, this is all just kind of a simple review towards the idea that ultimately we're going to have these huge data sets defining probabilities and statistics on these large data sets. Okay? But unless you kind of get this clearly in your mind what these mean, it's really hard to scale it up to large data sets. Okay. Then we can talk about concepts about events. In particular, 2 of them that are important to talk about are the union and the intersection of events. Okay? So suppose I have 2 events, E1 and E2, on some sample space S. Then I'm going to denote the union as E1, union E2, and the intersection as E1, E2. Okay? Now, again, very simple concept, so simple that what we're going to do right now, you ready, is draw a Venn diagram. Ready? When did you draw a Venn diagram? When was your last time? It's been probably a while. Probably haven't drawn one for a while. Like junior high? Have you drawn a Venn diagram since junior high? Nobody wants to volunteer Venn diagram drawing. Okay. Let's let this box represent my sample space. let's represent my MasterCard. Okay, no? Okay. Okay, there we go. It's okay, so let's call this event E1, this one E2. Then the union, of course, is going to be basically the two together. So it's all this space here. So if I had gray, if I could make, I'm a monochrome writer, so I can't do like grayed it out. But here you go. So E1, E2, that's the union together, and it still spans some subset of the full sample space. And then this little part here, that's the intersection. E1, E2. Okay? So that's a very simple picture to draw, but it actually is very helpful to think about probability events. By the way, what we talk about as an event, the union event, is we have an event and it's in the union, then it means it can be either in E1 or E2, or it can be in both, right? And then if you have the intersection, then it's an event that has to be satisfy both events, E1 and E2, okay, by definition. And it lives in this little space. Now, if these two circles don't touch, okay, so let me draw a smaller Venn diagram over here. Then here, there is no intersection. The union would still be the two areas. And what would be said about these is that these two events are independent. Okay? Part of what I'm building towards is this idea of what does it mean for events to be independent or dependent? Because ultimately, it's going to come into our ideas of statistical significance. When we start measuring data and talking about, does this data relate to this? I have a ton of data. I have temperature data related to flow of a velocity or a fluid or something like this. Are they related? You have to make a test about whether it's statistically significant, and really ultimately you're asking about, are these two independent variables or not? Okay? So here's the first talking about that in some sense. Okay? All right, so we'll come back to coin flips, and we'll talk about same kind of experiments we did before. So we talk about event 1 as being getting a heads, at event 2 getting a tails on the coin, then the union of these two events, right, is whether I got heads or tails, which is actually the full sample space, right? So if you're flipping a coin, if I look at the union of these two events, heads or tails, by the way, which are mutually exclusive, right? I mean, if I get a heads, it can't be partly tails, okay? Tails can't be partly heads, but the two span together the sample space, okay? And in fact, if you look at this, you can say the intersection between these two, the empty set, okay? So again, unless you can land this thing on an edge, there it creates problems. Otherwise, it's either heads or tails. And so the intersection of something is that it has to be both E1 and E2, and it cannot be heads and tails at the same time. Oops. Okay, so far so good? All right. Nobody's flipping coins yet out in the classroom? Not yet? Okay. Finally here, I think I dropped my note. Here we go. I said this is 2, 3. If you're tossing a dice, and if you let event E1 be 1, 3, and 5, and event E2 be 1, 2, and 3, okay, then the intersection, for instance, if I ask for the intersection of these two events, something that belongs both to E1 and E2, and you can see that 1 and 3 are in both. So that would be the intersection of these two events. Okay? And you can generalize these ideas by drawing even more fancy Venn diagrams with more circles, if you'd like. Okay? But that's a simple idea. Okay? Again, simple concepts, but they become sort of the underpinnings that we're going to build later on. Okay, so these are just events, sample spaces, and ultimately what we care about is the probability of these events occurring. Okay? That's really the big thing you're after, is you're wanting eventually to build up a statistics or an understanding of the probability of these things happening. And so now that we have the framework of events and sample spaces, then we can talk now about defining what probabilities are. Okay? All right. By the way, my notes will be on the web shortly. Like today's lecture will be up in about within an hour. You can go to the web page and download the notes, and there it is. I'm trying to tech them up nice for you. I would ask that as you're reading through and you say, this is totally wrong, that you tell me, or like if I spelled something wrong or I typed something wrong, it would be really nice to edit the notes as we go along. Because as you tell me stuff that's typos, I'll fix it, and then I'll just keep uploading the newest version, so by the end it'll be a perfect set of notes. Now in the past I've paid money for this, but that was because the notes actually were in pretty good shape. So it's really hard to find typos. It's probably not going to be very hard to find typos right now. So I can't pay money or else I'd be broke. Okay. Okay, probabilities. Defined on events. Let me switch pins. Okay. Typically, we're going to define this as, oh, that's nicer. It's a nicer pen. The probability that the event E happens. Okay? So we've defined some event E, and then we asked, okay, what's the probability of this event actually occurring? Okay? So we can calculate these things. Now, some properties about P of E. So first, it's between 0 and 1. Okay? If you put it in percentages, you multiply by 100, there's only a 100% chance of something happening. There's no 110% chance of rain, except for outside right now. It is raining 110%. It's giving it its all. Great way to start the quarter. Who loves living in Seattle? Yeah, see? Those are the people who've been here a little while. The rest of you, first-year grad, second-year grad, you're kind of like, how long do I have to go to graduate? All right. There you go, from 0 to 1. It either has no chance or it will happen. All right? And if you really want to say something strong, you'd say, with probability 1, it's going to happen. That's about as forceful as you can be. Okay? So that's how you win an argument. Whoever says with probability 1 wins the argument. So make sure to say it first. Try to be right if you can. All right. The probability of it being on the sample space is 1. Right? I mean, if you define a sample space where all outcomes live, and I do an event, it has to be in that sample space. Unless you completely missed part of the sample space. Like if you said, hey, I'm going to flip a coin, the sample space is heads, and you get a tail and you're so surprised. That's because you just missed your sample space. Now, by the way, again, in most experiments we're going to really talk about down the road, you don't know the sample space. That's the nature of, in some senses, class, which is to say, how do I extract anything meaningful anyway? When I just have data, how do I process it, make something meaningful? But again, we're assuming the best things here, which is we know all the stuff, we know all the events, we know probabilities. For any sequence of events, let's call them E1, E2, all the way to E of n. that are mutually exclusive. So that is E of I times E of j, the intersection of two of them, I and j are different, is the empty set. So if they're mutually exclusive, they're like balls in this Venn diagram that don't intersect each other. Okay? Then the probability of the union of these events from n equals 1 to n of these n events is equal to the sum of the probabilities of each event individually. Okay, some basic properties. By the way, we're going to talk about non-mutually exclusive events in just a second. All right, so let's talk about coin flips again. I keep going back to this. I try to stay consistent with examples this whole lecture through so that we always go back to pretty much the same basic examples because we've defined sample spaces, we've defined events, now we define probabilities. So for instance, in the first one, with a coin flip, the probability generating a heads is 1/2 if we have a fair coin. Okay? Same thing for tails. So this is always what we assume, right? You flip a coin, you get heads or tails with equal probability. And if you have an unfair coin, okay, suppose you have an unfair coin where you are twice as likely to get a heads, then you'd have something like probability of heads is 2/3, probability of tails is 1/3. Okay? So something like this. So how we define probabilities is another interesting idea, okay? We'll talk about that in a moment. 2 coins. What is the probability of getting 2 heads? It's like a fourth. There are 4 different outcomes: heads, 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 tails, tails, heads, tails, tails. And if they're equally likely to occur, then this is one of the 4 outcomes, and so your chance is a fourth. Okay? Same thing with a die toss. Then your probability of getting any of the numbers, 1 or 2, so forth, is 1/6. Again, with a fair dice. So this is the formal definition, right? But in some sense, there's a big assumption that went in right here. For instance, in your coin. I have a coin. I could pull out a quarter, and we could flip it, right? And so in some sense, this is the formal definition. On the other hand, in a statistical way of thinking, the frequencies, if you call it, there's people who, if you just do the experiment over and over and over and over and over again, the idea is if I flip a coin 1,000,000, billion, trillion, I just keep flipping coins all day long, and then the next day, and then keep going the next day, and I keep track of heads and tails. Then the idea is if I do it enough times, in some sense, that's what gives me the belief that, yeah, half the time it came up this, half the time it came up that. So how would you test a fair coin to begin with, right? I mean, in some sense, it's not like I give you a coin. How do you know it's not that? How are you going to test for that? Because if I do 3 flips and I get 2 heads once and a tail once, that doesn't mean anything, right? That you could be just a fair coin. It doesn't mean that it's obeying these kind of statistics. Okay? So we'll assume we'll assume sort of in a very deliberate way that these are kind of intuitive concepts that we believe we have a fair coin, and it's half likely to be that or this. But in the frequencies point of view is that you're going to do an experiment over and over and over and over again to determine what these would be to begin with. Okay? Okay. A couple more things that we can comment on here that are important. First, the complement. For an event E, let me give you an example from the movie Derek Zoolander. They'll be looking for us, right? But they won't be looking for not us. You have an event, and you have the complement of the event. E and E complement. Us, not us. Sweet. We're going to talk about Zoolander all the time. He's one of the giants of the field. All right. So basically, when we define probability, we might have, for instance, to define a probability, by the way, the union of the event and not the event, or its complement, is the whole subspace. Okay? Right? So whatever E doesn't take up in the sample space, E complement does. And then we can ask the following question. So first of all, the probability of being on the sample space is 1, but this is also the union of E and EC. But see, E and E and its complement are mutually exclusive, which means I can write this as the sum of. It's a very obvious result, which is, if you look at this, you say probability of E is equal to 1 minus. The probability of something happening is 1 minus it didn't happen. Okay? It's an intuitive result. All right. So that's one thing, the complement. Now let's talk about events that are not mutually exclusive. And I can ask about the probability of the union of these two events. Now, if they were mutually exclusive, we would get this. But that's not right when they actually are not mutually exclusive. And just to see it, it's pretty easy to see from our Venn diagram. When you look at the probability of being in E1, it's this whole circle here. When you look at the probability in E2, which is what you're asking, it's this whole circle here. You double counted the intersection space. Okay? So you have to subtract off that one intersection space. All right, so there you go. That is an important result, and we'll be using it. Okay? So when you ask about these probabilities of unions, make sure to understand if they are not mutually exclusive, you have to watch out for that intersection in your calculation. Okay. Questions so far? We're flying along. Is this ringing a bell to a lot of people, hopefully? Hopefully a lot of stuff is sort of somewhat refresher, somewhat intuitive. We're hoping to build, the concept of the course is going to be to build a lot on your intuition, set it down in mathematical framework in this first week, so that when we start off next week and head off into the wild blue yonder analyzing data, that you have this at least as an anchor to go forward on that. Okay? All right. So we continue. With conditional probabilities. Okay, this is typically defined if you have some event E1, some of another event E2, and you can ask the following question. here's how a conditional probability is written. What is the probability that E2 occurs given that E1 occurs? Okay? So, for instance, you could ask the following question. Here's a conditional probability. What are the chances I make it to Manhattan given that I've actually landed in Newark? You might say, of course he's going to go to Manhattan. Why would he go to Newark, New Jersey otherwise? So it might even say 100%. But there's some chance, like, you know, the bridges all fell down and the train wasn't running that day, that I might not make it. And I'd be stuck in Newark. Okay. But it's close to 1. So that's the idea. You ask the question, and oftentimes E1 places an important constraint on E2. Okay? Now, let's talk about how would we calculate this. So first of all, the event that it has here, what I'm saying is what happens that E2 is actually satisfied given that E1 is satisfied. So in other words, I'm asking for an event that lives in the intersection. Right? It has to have both E2 and E1. But I'm asking to calculate this intersection on a restricted domain. In particular, I'm restricting it now to the space where E1 occurred. Okay? So this becomes effectively my new sample space for determining whether E2 happened. I'm already in E1. That becomes my sample space. That's my normalization in some sense. And then within that sample space, I look to see, does E2 also happen? By the way, obviously the formula, you know, we have to have the probability of E1 happening better be bigger than 0. You can only be divided by 0 anywhere here. Okay? So let's do some examples on conditional probabilities. All right. So, coin flips. Here's the question. What is the probability? Got to get 2 heads. If already 1 is a head. Right? So what I'm asking about is E2 is the event that I have 2 heads. And E1 is the event I have 1 head on a coin. Doesn't matter which one. Just have at least 1 head on a coin. So actually, at least. It's an important. Okay? The one thing I don't like about teaching this stuff is that you have to write a lot of words. Okay. I have rules about that, but we'll get into that later. Okay. I'm writing words. So you say, okay, so I'm looking for this. That's what I'm trying to calculate. What is the probability I get 2 heads given that I already have 1? According to this formula, what I'd look for is the intersection over the intersection of E2 and E1 and the fact that I just have at least 1 head. Well, what are the probabilities here? By the way, so the intersection of these two is if I have the probability of basically getting 2 coins, heads, heads. That's the intersection of the event E1 and E2. Okay? And the intersection, and the probability of getting 1 head on a coin, well, that is the probability of either having heads, 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 tails, or tails, heads. I don't know if I have the right number of parentheses, but who cares? Okay, so there's 3 possible outcomes. Now, if it's a weighted, if it's a coin, those fair coins, then my probability of getting heads, heads is a 4th. My probability of getting ahead on any one of the coins, at least one, is 3/4. So my total probability is 1/3. All right? So it's a simple calculation. Anyway, I flip coins, have conditional probabilities, I have 1/3 probability. If I know that one of them is a heads, my chance of getting 2 heads is 1/3. Okay? So that's the idea of the way this works. Let's do one more example, and then we'll talk about what are we doing on time. We'll skip that example. It's in the notes. You can come back. It's a stupid card trick. You pull out a card, and anyway, and you do some probability on it. It's in there. It's another one. Talk about independent events. So the idea is just like it sounds. How do I know if I have an event 1 and 2 that they're essentially related or not related? And that's the idea of independence or dependence of the events. And so a formal definition of this is the following. If I look at the probability of the intersection, this product, if that holds, then they are independent. Okay? Moreover, if you look at this formula here and you say, okay, let's come back and apply that formula to right here on a conditional probability definition, then the intersection PE2E1 becomes PE2 times PE1. The PE1s cancel. And what you get here then is PE2 conditioned on E1 is equal to just PE2. This is probably the strongest, most what do you want to call it? A transparent statement of probability, which says, what is the probability that E2 happens given that E1 happens? If it's the same as that just the probability that E2 happened, it doesn't even care about what happened to E1, that means that these are independent events. Okay? So that is the statement of independent events. I give him, yes, Jake.
So then I think we should correct something you said earlier. Before you drew a Venn diagram and you drew 2 disjoint sets,
Yeah.
and then you said these are independent events.
No, I meant to say mutually exclusive. Sorry. Can we go back and delete the tape? I never said that. No.
I thought you said we were going to get smarter by the end of this.
We're supposed to. But who knows? Like you said, we start off with 0 expectations, right? Everybody was in here just like dreading being here, like I'm not going to learn anything today at all. And so we start with there, and I hope every day everybody comes like that to class, because then I can only go up. Okay? As soon as you start having expectations, I can only, I don't stay even or go down. Okay. Something about that statement, you can only lose, right? Okay. I better go with that, independent events. I got a little example there. You can go through it. But I do want to get to one other issue here. It's related to what's called Bayes' formula. There's a whole branch of statistics, Bayesian statistics, blah, blah, blah. Talk a little bit quickly here and actually give a nice little example. An event E1, suppose we have 2 events, E1 and E2. Then the event E1 can be expressed as the following, as the intersection of E1 with E2 union the intersection of the complement of E1 with E2, which makes sense. Like the event E1 can happen with E2 or without E2. Okay, but that's the whole space of E1. Now, at first, that might seem kind of an awkward way to write things, right? But by the way, these are, in fact, mutually exclusive events. So if I look at the probability of E1, I'll show you an example where this comes in very handy, and then you'll see why people would look at it this way. Because they're mutually exclusive events, I can write out this probability as the sum of these things. Okay? And then I can start using my definition of basically conditional probabilities. And let me write this out because I want to get to the example before the bell rings. Looks something like this, and I can finally replace this by 1 minus PE2. So essentially, this is what's related to what's called Bayes' formula. And what it states is basically that the probability of event 1 is basically, it's an average of a weighting of the conditional probability of 1 happening given A2, weighted with an average of E1 and E2 complement happening, weighted according to the probability of those two events happening. Okay, seems a little kooky. Why wouldn't I just stay with PE1? Final example that I want to give. And I think this one's actually very important. And, by the way, if you ever decide to get pregnant, you, your wife, your kid, whatever, whoever's there, okay? You're pregnant, you're going to the doctors, and you got a kid, and there's all these tests they do, and there's a chance that they test all these things. So before you get there, it's always a good idea to have a little talk about statistics. Here's why. I have a 95% chance, if I give this test, of determining a certain disease is present. That sounds awesome. I'll get to you in a minute. I've got to finish the example. However, here's the thing, false positive. 1% chance only. So, if you don't know that much about statistics, you say, hey, this test looks pretty accurate. So if I get a positive, I should get really super worried. Okay, that's the typical inclination. However, you can ask the following test. If 0.5% of the population actually has the disease, then even if you get tested positive, only 32% will actually be positive. Okay? I'm not basically using these formulas here, examples in here. So in other words, if you get the test, it's only 32% chance. Now, by the way, this illustrates something very important. Because suppose the disease is not 0.5% of the population, but only 1 in a million people have it. If 1 in a million people have it, then instead of 32%, if you test false positive, your chances of having it are still 0.01%. Now, here's the problem. When you see this, you go, look at that. That's an amazing probability of getting this thing. But the fact is, there's this. It's a very rare disease. And this is why rare diseases are actually tremendously difficult to test for. And the problem is that someone sitting there who has no knowledge of statistics, not you, of course, now, because you're so smart, you might get kind of concerned that you have this 1 in a million disease when after you get tested positive, your chances are still 0.01. So understanding, and by the way, again, when you're there with your wife, this is a bad time to start explaining statistics to her. I give very good advice sometimes. There's one of them. Take it down, write it down. All right. Have a good day. I'll see you Wednesday. Notes will be up soon.